Hi everyone, my name is Ravi Tangirala. I'm a R&D Program Manager at Nanosys. Hoping to see everyone at the QD Forum in Portland this week, but since the flavor of the day is doing things online, we decided we would bring this presentation to you online instead of having this in person. So I will be talking about quantum dots for use in color conversion applications. Let me begin with saying a little bit about Nanosys. We are the world's leading quantum dot supplier. We make quantum dots for many different applications in the display space. Nanosys is an innovation leader with among the largest patent portfolios related to quantum dots and nanomaterials. We have the world's largest quantum dot manufacturing facility, and we are able to manufacture at the lowest cost that you can get these materials for. And our customer base includes the cream of the display industry. We work with all the top tier companies in the display space. Nanosys has a three-pronged business model. We primarily are a manufacturer of quantum dots, and we make the world's best quantum dot materials and sell those. We also work with our partners for designing and licensing manufacturing rights for different components used in the display industry that contain quantum dots. An example of that would be QDEF, or quantum dot enhancement film. And we continue to work to develop innovative technologies for the future display applications. So let's talk a little about quantum dot displays. At this point, there are over 100 unique products on the market which contain quantum dots, and both throughout last year as well as at CES this year, 2020, there were a lot of new models that were introduced. We were highlighting some of the new products here. Quantum dots today are used in TVs, monitors, other kinds of displays, mobile applications. And a huge number of display manufacturers are introducing products that contain quantum dots. We're getting to the point now where quantum dots offer, while they've always offered the high quality comparable to OLEDs, quantum dot displays are now at the price point where they're competitive with conventional LCDs as well. And this is great news for consumers. Couple of examples shown here where at Black Friday sales in 2019, you could buy really premium TVs for less than $400 containing quantum dot displays. And this is really great news for consumers because it really expands the choices that are available at a very high quality. And while OLED TVs are generally considered to be really the premium segment in TVs, there are market projections out there that say that the quantum dot containing TVs will outsell white OLED TVs in the coming few years and continue to outsell over the next few years. So this is really an exciting time to be working in quantum dots in the display space. Nanosys, as I mentioned before, is not simply a manufacturer of quantum dots, but we also work on upcoming display technologies. And this is just a quick look at our product roadmap. The products that are on the market today are quantum dot enhancement film, QDEF, and quantum dots on glass. Both of these approaches use a mixture of red and green quantum dots that go on top of a blue backlight. The output is a perfectly controlled red, green, and blue light, which is then pass through the different components of the display panel to make up displays with perfect color and high brightness. The next step on the Nanosys roadmap is QD color conversion, which is the topic of this talk, and you will hear a little bit more about it in the next few slides. Finally, we think the future is going to be with electroluminescent quantum dots instead of photoluminescent quantum dots. And at this point, that would really open up the market for lots of different kinds of applications beyond what's available today. So let's talk about quantum dot color conversion. Here's a animation to show how the quantum dot color conversion works. First, let's begin with QDEF, or quantum dot enhancement film. As I mentioned a minute ago, quantum dot enhancement film contains a mixture of red and green quantum dots which are mixed into a resin. This goes on top of a blue backlight in a TV set. The blue goes through, is partially absorbed by the QDEF and partially converted into perfectly controlled green and red peaks. This mix of white light goes through the LC panel and the other components of the display panel, and then converted into red, green, or blue at the front of the panel by the color filter. Now, in the QD color conversion, the QDEF, the quantum dots, instead of being integrated into the QDEF, are integrated at the front of the panel, replacing the color filter. As a result, the blue light that comes out of the backlight goes through the LC panel and gets converted to red or green at the front of the panel instead of being filtered out. The blue subpixel is left without quantum dots, and so the blue simply goes through the blue subpixel, whereas in the green and red subpixels, the blue light is perfectly converted into green or red light. In QD color conversion, the quantum dots are patterned at a subpixel level, and this layer replaces the passive color filter array that's present in conventional displays. By converting from a color filter to a QD color conversion layer, you can get much higher power efficiency or brightness. There are other benefits like a much wider viewing angle and a hybrid emissive display. All kinds of displays can benefit from the use of QD color conversion, including LCDs, micro LEDs, and OLEDs. And Nanosys quantum dots have been optimized to be compatible with different approaches like inkjet printing or photolithography that are used for depositing and patterning the QD color conversion layers. So the main difference is in the ways that quantum dots affect LCD devices is by using a QD color conversion, you can get a much higher device efficiency because the white light is not simply being filtered by a conventional color filter, but the blue light is actually being converted into green and red at the front of the panel. Due to the conversion happening at the front of the panel, the viewing angle is much wider, and this is a problem that is particularly present with LCDs, where typical LCDs have a very poor viewing angle, but by having quantum dot color conversion at the front of the panel, you can get a much higher viewing angle, which simply means that the colors show up the same whether you're watching from in front of the display or from the side. Now, the use of QD color conversion in LCDs is complicated by the fact that the LCD design itself has to be changed and the in-cell polarizer needs to be introduced into the LCD. This has proven to be quite challenging. However, quantum dot color conversion is not limited to LCDs and can actually be applied to any type of blue light source. And we'll look at a couple of examples here. So one example is with OLEDs. Now, your typical white OLED contains either a blue OLED layer capped with the white phosphor, or multiple layers of red, green, and blue OLED materials that are stacked on top of each other. The white light that's generated by this OLED stack goes through a color filter layer and is filtered out into individual green, red, or blue subpixels, which then come out of the display. In the case of QD color conversion, instead of using 3 different colors of OLED materials, we would just use one color, a blue OLED, and replace the color filters with a QD color conversion layer. So the blue light for the blue subpixel would simply go through the blue QDCC layer. For green and red, you can simply use a blue light source, which is converted with very, very high efficiency at the QD color conversion layer. And so you get a perfect white light forming at the front of the display panel by using this approach. By replacing the 3 different OLED emitters with just one material, there's also a lot of implications for reducing cost of these devices. In addition, because quantum dots allow you to have much higher efficiency, because the color conversion efficiency with quantum dots is much higher than what you would get with a conventional color filter, the overall device efficiency goes up. The color gamut is also potentially much wider through the use of quantum dots because of the wavelength tunability and narrow line width of quantum dot emission. There are some challenges, of course. Despite all the benefits from the use of quantum dots and OLEDs, getting a high efficiency, long lifetime blue OLED material is a challenge that the industry is working with. And as far as the quantum dots are concerned, one of the big requirements for the quantum dots, which again does present a challenge, is the need to improve the blue light absorption using a cadmium-free material. The role of Nanosys in this technology is threefold. Mainly, we design and manufacture heavy metal-free quantum dots that can meet all of the requirements for this application, including high blue absorption, high quantum yield, and a targeted wavelength and full width half max. The quantum dots needs to be stable in all of the processing conditions that are used for the QD color conversion. We also design the ligands that are used on the quantum dots, which allow the QDs to be mixed with the printable inks or the photoresists that are used for depositing and patterning these devices. Now, these ligands need to be able to impart solubility in various media, polar or nonpolar. At the same time, they need to be small enough, low molecular weight enough that the mass added from the ligand is not significant and it doesn't start impacting the viscosity of these things. And finally, we need to do all of these things, the QD production as well as the ligand implementation, at a scale where we can provide a consistent product at the lowest possible cost to our customers so that the market can adopt these technologies. So I briefly mentioned blue absorption of the quantum dots, and in the next few slides, I will talk about why the blue absorption is so important and how it starts impacting the display quality. So in a quantum dot color conversion film, a relatively thin layer, 10 to 15 micron thick layer, is used for absorbing almost all of the blue light from the backlight and converting it at high efficiency into green and red. The output, if you look at the 3 subpixels together, would look something like the picture on the left, where you have a narrow blue light that comes out of the blue subpixel, green that comes out through the green, and red that comes out through the red subpixel. If you have any amount of blue light leakage in the green and red channels, then that starts to affect the color gamut quite significantly. So you cannot have crosstalk between blue and the green and red channels. At the same time, you cannot have crosstalk between the green and red channels either. So the green cannot be leaking into the red and vice versa. So getting rid of this leakage between channels is extremely important. Now, the blue leakage is a function of the QD layer itself. And this is an area where the color gamut can be very significantly affected by the QD properties. We have done some modeling at Nanosys that shows us that if you can eliminate the blue light leakage in the green and red channels, or reduce it down to the level of 0.1%, you can actually get very high BT2020 coverage, over 95%, if the wavelengths are optimized. For this to happen, the required optical density within the QD layer is very high, something like OD3. Based on all of these requirements, we have come up with a metric that we call OD450 per mass. The 450 here refers to the wavelength of the blue light that's used in these displays. And what this metric essentially means is for a given mass of quantum dots, whether that's on a milligram basis or a gram basis, how much of the blue light is absorbed. So from this table, to get 0.1% blue leakage through the red or green subpixel, the OD per mass that's required for the quantum dots is over 1. If you can tolerate a little bit more blue leakage, if you have 0.5% of the blue leaking through the red or green channels, you can see that the BD 2020 coverage does come down, but the OD per mass requirement for the quantum dots is a little bit more relaxed. With even higher blue leakage of 1%, again, the BD 2020 coverage comes down even further, but the quantum dot requirement does get a bit relaxed. To see why the blue light leakage has such a big impact on the color gamut, take a look at the graph on the right. This is an idealized case where you have no leakage at all in the green and red channels at all the right wavelengths. Now, if you only have 0.5% leakage, you can see that the red point is now starting to pull in. So if you have a slight amount of blue leakage in the red channel, that starts shrinking your color gamut. And if you have a 1% leakage in the green or red channels, then that reduces your color gamut even further. So the point of this slide is to say that the blue light leakage is really a critical factor that impacts the color gamut in these displays. So the blue absorption is critical to performance. And so to get a very high level of blue absorption, the quantum dot loading needs to be very high in these QD color conversion films. So again, like I said, the figure of merit that we use for QD performance is OD per mass. And looking at the absorption spectra for indium phosphide quantum dots, you can easily tell that the red quantum dots are, red indium phosphide is an inherently much better absorber of blue light than green is. And on the previous slide, I showed some figures where to get 90% BD 2020 coverage, you can tolerate 0.5% of blue light leakage. The OD per mass required is on the order of 0.7 or 0.8. Red indium phosphide quantum dots either meet this requirement or get very close. But green quantum dots lag quite far behind in terms of the blue absorption itself. And this is simply a material property or material limitation that the green quantum dots just do not absorb blue light well enough. Now, of course, you can increase the quantum dot loading to such an extent that you can start absorbing close to 100% blue light. But this is not practical for a variety of reasons. Mainly, the cost starts becoming prohibitive. The viscosity goes up. And there are other constraints that come into play which limit the amount of quantum dots that can be included in the QDCC layer. And so one approach that a lot of the display makers are looking at, and which our model also suggests may be the right way to go, is to have most of the blue absorption happen in the QD layer. And from our modeling, we think that this is somewhere between 95 to 98% of the blue light being absorbed in the QD layer. And then an additional layer, additional color filter, pigment-based color filter is added on top of the green and red channels to eliminate that little last bit of the blue leakage in the green and red subpixels. Now, this additional color filter layer is also needed for preventing excitation of the QDCC layer by ambient light, because the ambient light can start making the QD layer luminous and start looking colored. So to prevent that from happening, you probably need an additional color filter layer anyway. Now, the use of this additional color filter layer is not without trade-offs. No color filter material is 100% transmissive. And by applying any color filter layer, there is a risk of absorbing or filtering out some of the light that the subpixel is expected to transmit. Green is more susceptible to this. And so what I really mean by this is if you take a green subpixel, you have a green QD layer, and then you place a green pigment color filter on top of it. The green color filter will absorb some of the green light that's put out by the QD. The thicker the color filter, the more loss you have in the green light, and so the overall panel brightness starts getting affected by this. So really the best solution is to improve the inherent blue absorption properties of the quantum dots, particularly for green, because green is more subject to this kind of transmission loss effect. And this is a core area of R&D at Nanosys, and this is an area where we have put in a lot of effort. We actually have a new material that is under development right now, and hopefully you will hear more about this material in upcoming presentations and forums. But Nanosys is working on an entirely new composition, heavy metal-free, cadmium-free material that per gram has a much higher absorption of blue light than indium phosphide green does. And so here's some representative data where for a given QD loading and a given film thickness, the new material can absorb a much higher amount of blue light than indium phosphide does. The y-axis here is blue absorption, but to look at it helps to think about this in OD terms as well. So 90% absorption is OD1, 99% is OD2, and so on. So you can see that a 12 micron thick film of indium phosphide absorbs around 92% of blue light, whereas with the new composition, the same thickness with the same QD loading absorbs 99% of blue light. This new material is tunable in wavelength. We are able to tune the wavelength from 530 to 545 nanometers. Has a low full width half max in film, which is also important for getting a good color gamut. Like I said before, heavy metal free, no lead or cadmium. And this material is also compatible with printable ink formulations. You will hear more about this in the future. I want to switch a little bit to the ways in which the quantum dot color conversion layers are fabricated. As I've said before, the QD color conversion can be applied to any display that has a blue light in it. There are multiple ways of fabricating the QDCC layers as well. You can go through additive manufacturing approaches such as inkjet printing or lithography approaches such as photoresist, and each of them has their own benefits. The benefit for the photoresist approach is mainly down to the resolution that can be achieved. Because these are conventional photoresists that are used in the display industry and other electronic industries, you can achieve resolution of 5 microns or below, or feature sizes of 5 microns or below. And equipment that is available in fabs all around the world today can be used for the photoresist approach. And so that presents a pretty big that's a pretty attractive benefit from using the photoresist approach. On the other hand, the inkjet printing does need new equipment, new printers to be installed, but is a overall more efficient method because there's a lot less waste of material. the processing conditions are gentler, fewer processing steps, less stack time, and so on. So both approaches have their own pros and cons. Inkjet printing, we have worked with ink manufacturers, and the way in which these films are fabricated by inkjet printing is that you first take a substrate, a glass substrate, which has wells patterned into it. Now, you could also deposit an additional color filter, if needed, into these wells before the QDs are inkjet printed. The thickness of the QDCC film is controlled by the height of the black matrix pattern. Inks containing the quantum dots are inkjet printed into these wells and then cured either by UV irradiation or by other means. And Nanosys has worked with ink manufacturers for designing a variety of inks that are used on most of the common heads that are available today. Inks can be solvent-free or solvent-based, and again, there are pros and cons in each case. Solvent-free inks give you 100% fill factor in a pixel, so these pattern wells can be filled with ink, cured immediately, and you can achieve your final thickness in one step. Solvent-based inks have more flexibility with respect to the ink design itself, but you don't get 100% fill factor. Multiple passes are needed for achieving the final thickness. But again, both approaches are possible and have been demonstrated. Here are some examples of inkjet printed blue, green, and red subpixels, and this was some work that our partner DIC has done. Again, using cadmium-free quantum dots, printing is done in air, curing is done in nitrogen, very high materials utilization, and you can make inkjet printed features that are on a size scale that's relevant for large area displays. On the right, on the bottom right, you can see that the viewing angle that can be achieved for these printed subpixels is actually very high, and you can get very, and this is a function both of the isotropic emission from the quantum dots as well as the other components that are added into the ink. Here's an example of RGB pattern inkjet printed film, again, that DIC had made. And again, the features here, the feature size here is relevant for large area TV display applications. The other option for QDCC fabrication is using the traditional lithography approach. And in this approach, the quantum dots are mixed with a negative photoresist, and the way the films are made are by spin coating typically, but although other methods could also be used, patterning through through a mask by UV irradiation. You rinse the film with an aqueous developer to remove the areas that are not cross-linked, and then the films are baked to solidify the features. To get your second color, you start over again and then deposit the second color, irradiate through a mask, and basically go through the same processes to get a patterned film. All of the patterning, all of the handling here is done in air, including high temperature processing and UV exposure and wet etch with the developer solutions. And Nanosys quantum dots have been designed and have been optimized for use in these kinds of processing environments. Here's an example of a demo that we had made a couple of years ago where we patterned the blue, green, and red subpixels. The green and red here contain quantum dots, whereas the blue simply contains the scattering material and is the blue backlight coming through. Again, all of the processing is done in air, including the high temperature baking, exposure to UV, exposure to aqueous developer, and so on. We have partnered with Sumitomo Chemical for providing these QD photoresist mixtures to various partners. And currently the capability is down to the order of 3 micron resolution. Where this QD photoresist approach is really attractive is for micro LEDs, because the size requirement for micro LEDs is typically much smaller than it is for the TV type of application. So in the micro LED option, you can coat the quantum dots directly, either on glass at a small feature size, or the quantum dots can be coated directly on top of the micro LED panel. We show the micro LED stack as a generic structure here, but there are lots of approaches that many companies are working on, and the quantum dots can be applied to all of these cases. The big benefit from using quantum dots for micro LEDs is the simplification in the manufacturing process and the high yield that results. Then the reason that the manufacturing process is simplified is that one of the current ways of forming an RGB micro LED panel is to make the red, green, and blue separately, dice the 3 wafers, and then pick and place the red, green, and blue LEDs into place. With quantum dots, this process can be simplified quite a lot. You just need the blue micro LEDs, and then the red and green are patterned on top of the LEDs themselves. And so that really can drive the cost down and complexity down. Again, here's an example of features using quantum dot photoresist that have been the features that are relevant to the micro LED size range on the order of 3 to 4 microns. Finally, we've also partnered with other groups to look at other ways of forming these very fine features that are of interest to micro LEDs and related application. Here are some examples of patterns that have been made by transfer lithography, and by using methods like these, you can make sub-micron features quite easily, and very high aspect ratio features as well. So in summary, QD color conversion is the next step in the evolution of quantum dot-based displays. And really, this can be applied to any display that has a blue light source in it. All of these displays can benefit from quantum dot color conversion. Specifically, in the case of LCDs, you get much higher device efficiency and wider viewing angles through the use of QD color conversion. OLEDs can benefit from the higher brightness that is possible through the use of quantum dots, combined with the high contrast that OLEDs can achieve. Add to this the wider color gamut that quantum dots can achieve because of the emission properties. And there are reports out there that also consider the lower cost of the QD-OLED hybrid display compared to the white OLED. Micro LEDs can benefit from simpler processes and lower manufacturing costs, as well as wider color gamut and higher efficiency through the use of quantum dots. We really think the big innovation that is going to expand the range of applications and geometries is going to be the development of new materials with enhanced blue absorption. And again, this is something that we look forward to presenting more updates on. So that's all. Thank you very much.